Hello and welcome to Fast Track Chiplet Integration with Streamlined UCIe's Electrical Layer Analysis. Today's webinar is sponsored by Keysight Technologies and produced by SmartBrief. My name is Scott Becker. I'm from SmartBrief, and I'm excited to be your moderator for this special event. Now, before we get to today's great session, we do have a few housekeeping items that are going to help you get the most out of it. First off, we want this to be an informative event for you. So we highly encourage any questions in the questions box in your webinar control panel. Not only will we have team members responding to questions during the live event, but we'll also have a dedicated Q&A session at the end of the presentation where we'll discuss in greater detail some of the top questions that you ask. That Q&A panel is also the place to let us know about any technical issues that you might be experiencing. A browser refresh will fix most audio, video, or slide advancement issues, but if that doesn't work, just let us know in the Q&A and we'll provide further technical assistance. Now, second, in the handout section of your webinar control panel, you'll find that we've got two resources there that I'd like to call your attention to. There's a link to an application note on how to detect signal integrity issues in chiplet designs early, and there's a link just to learn more about Keysight technologies in general. So check those out. Now, third, at the end of this webinar event, we'll be awarding a $250 Amazon gift card to one lucky registrant. Of course, you must be in attendance during the live event to qualify for the prize. Official terms and conditions of today's prize drawing can be found in the handout section. Just scroll to the bottom and you'll find the link with the details there. Okay. So with all that housekeeping out of the way, let's get to today's fantastic session. It is my pleasure to introduce you to our presenter today. We have Tim Wang Lee, who's a Signal Integrity Application Scientist at Keysight Technologies. I'm going to turn things over to Tim to get us started.
Hello, everybody. Welcome to today's webinar, Fast Track Chiplet Integration with Streamlined UCIe's Electrical Layer Analysis. My name is Tim. I'm a Signal Integrity Scientist at Keysight. I will be your guide today. I will take you on a signal integrity journey while giving you a view of the UCIe standards. On the signal integrity side, we will cover crosstalk, frequency-dependent loss, and some equalization. On the UCIe side, we will talk about the electrical layer in the standard. By the end of the webinar, you will understand why the industry is shifting to the chiplet design, have some knowledge about the electrical layer of the UCIe standard, and how to find the right software to help you analyze your electrical layer. A little bonus, I will also throw in a demo of a 3D EM analysis inside the chiplet designer. Let's go. Before I start, I would like to set the stage by describing the traditional chip design process. It starts with the schematic, where the designer places electrical components and ensures the performance requirements are met. Once the schematic is ready, engineers translate electrical components into the layout that will be printed on the wafer. The die from the fabricated wafer will become a chip. Here is a cross-section of you. Now we have the background. Let's take another look at why chiplet will improve the cost and performance of the chip production. Shown here is the monolithic approach, where 4 different functions are in one big die. We can see there's function A, B, C, and D. The chiplet design philosophy will break down these 4 functions into 4 different dies. This is how it looks like on the wafer. Now, if there are 4 defects on the wafer for the monolithic approach, and yes, there will always be defects, the big die would have a yield only 66.7% if we do the calculation. From design 12 chips, produce 8 chips, boom, the yield is 66.7%. On the chiplet design wafer, given the same 4 defects, we'll have an yield of 97.3% because the die sizes are smaller. When one fails, it does not impact the entire production that much. This example shows that the monolithic approach is now of a higher cost and risk, whereas the chiplet design philosophy has a lower cost and lower risk. In a recent AMD presentation, it showed that the cost of a hypothetical monolithic die designed with a 7nm node would cost almost twice as much. This means that adopting the chiplet design can reduce your cost a lot. Here's a summary of what we have discussed so far. The monolithic die requires a larger mask that is close to the fabrication limit. It has a lower yield and higher cost. On the other hand, the chiplet design philosophy can maximize the wafer usage. It has a higher yield, lower cost, and it's very easy to scale. That's why the industry is shifting to the chiplet design philosophy. Now, I know what you're thinking. If the chiplet is so great, why are we not doing it before? We know in life, there is no free lunch, even in the chiplet case. The complexity of the chiplet design is within the communication between the dies. That is why a lot of standards of the die-to-die interface are being discussed and rolled out right now. Today, we'll be focusing on the UCIe, the Universal Chiplet Interconnect Express. Here are some basics of the UCIe standard. And I promise, after we talked about the basics, I will show you the link example that I created. Everything started with two different package types, the standard package and an advanced package. Now for each package, they have the same basic unit, that is the module. In the module, there's a main band and there's a sideband, which we'll discuss a little more later. And for the data rate, we have a selection from 4 gigatransfer per second, 8 gigatransfer per second, all the way up to 32 gigatransfer per second. Here is a quick showing of what the signal will look like in the standard package. For the main band signals, there are 16 TX data lines, 2 TX clocks, 1 track for valid, and 1 track for track. For the sideband signals, these are signals where we do link training and configuration. 1 for the data and 1 for the clock. Also, the power, always on power, and I/O supplies are also in the sideband signals. Symmetrically, on the receiver side, we will see the same signals coming through, the 16, 2, 1, and 1 on the RX side. So these are symmetrical. And notice these are unidirectional lines. When the TX will go straight to RX. Here is a reference of all the signals in a standard package, mainband signals and sideband signals. And here I want to note that the sideband signals are for initialization, link training, and configuration. These are the low-speed buses. For the advanced package, we can see things get a little more complicated because, well, it is advanced. We can have 32 to 64 TX data lines. On the sideband, things are mostly the same, but I want to focus on here is the additional track and clock repairs and redundant data that is in the advanced package. Moving on to the signal list, we see that this is definitely more involved than the standard package, and it provides more redundancies to correct errors. Finally, I want to close out the discussion on standard and advanced package by comparing the size. This is an example to scale. We have the width and the depth of the standard package. And here is the advanced package to scale. The 5-dimension depth is an informative parameters and depends on the bump pitch, while the width, based on the standard, it must match the spec for advanced package. Overall, for compatibility, it is good for you to make sure the width is within spec. Now I'll show you the comparison between the standard and advanced for bump pitch, channel reach, and raw bit error rate. For the bump pitch, we can see that the minimum for standard package is 100 micron, and for advanced is 25 micron. And the channel reach are definitely different. The advanced package has only one channel reach. It has to be short. Moving on is the linked example that I promised. So for this link example, we'll look at a standard package with the chiplet bus transmission line in the middle. And we'll send signal through and look at the eye, and we'll gain some insights on signal integrity. They are the crosstalk, frequency dependent loss, and equalization. First, let's start with the TX. It's a single-ended unidirectional data line. First, we'll note that the unit interval is 41.67 picosecond, like we can see, right? Everybody can really read that scale and tell me it is 41.67. If you take the inverse of that, 1 over the unit interval, it is the data rate. That would be 24 gigatransfer per second. Now in UCIe, it's not enough that you support this data rate. You must support all the data rate below the chosen one, which are 16, 12, 8, and 4. Now let's take a look at the voltage swing. Now on the right hand side, I've noted my voltage swing is 0.6 volts, which is larger than the recommended 0.4 volts. So here I made a note. The TX voltage swing has to be larger than 0.4 volts. Now there's one thing though that I'm not doing quite perfect according to the standard. That is the TX voltage. Typically, it's recommended to stay below 0.85 volts. So the interoperation with future process nodes would be nicely transitioned. Now let's take a look at the clock. We have these interesting shapes on the left-hand side here, and soon we'll know why they're there. So starting with the data rate on the right-hand side, we can take the half of it and get our clock frequency. That is the 12 gigahertz. In UCIe, we have two phases for the 12 gigahertz. It's a half rate, 90 degrees and 270 degrees. And here is a plot of the half rate clock. Now for higher data rates, like the 24 gigatransfer per second, 32 gigatransfer per second, they must support the quarter rate clock. Right here, shown here, is the quarter rate clock at 6 gigahertz. Next, we'll look at the termination. For a standard package, we'll have a TX and a terminated RX with between 45 ohms to 55 ohms. For an advanced package, however, once we have the TX, the RX has to be left unterminated. And the I would look something like this: terminated I and unterminated. The reason being, A, unterminated RX will generate a larger voltage swing because the constructive interference at the receiver. Without a resistor, there will be no loss. Moving on to our link setup on the transmitter side, we have our 20 transmission line for 16 data lines and lines and valid and track on the right here. On the left, we will create a chiplet die component and set up 20 TXs and send the data through these ports. On the right of these transmission lines is the RX data, where we'll put another chiplet die and corresponding receiver data lines, clocks, and valid and track. Here is a summary of the simulation setup. In the middle is our channel. On the left, we will have the 24 giga transfer per second in standard package going through 20 transmission lines and receiver terminated at 50 ohms. Then most of the time today, we will focus on traces 6, 7, and 8. And we'll look at all these signal integrity metrics like I diagrams, VTF loss, crosstalk, and what is VTF? We will talk about it later. It's voltage transfer function, very special to UCIe. But before we start anything, I always remember my PhD advisor, Eric Bogatin's rule number 9. You have to anticipate before you measure or simulate. Based on this setup, of course, I would anticipate, well, my eye going in at the TX is open, and my eye at the RX with the UCIe eye mask is also open. That's my expectation. We expect the eye to be open. And let's see what the simulation says. The simulation says, on the left, it is open, but looks kind of interesting. On the right, however, it is pretty close. It's close to the eye mask. The density, eye density, is very close to the eye mask. So here, the simulated eye is almost close, a little different than expected. Let's take a closer look at the received eye with a UCIe eye mask. Here's the standard package operating at 24 gigatransfer per second. Here is the eye mask and the contour with the vertical division 100 millivolts. The simulation condition based on the standard, for the eye mask should be noiseless and jitterless. So in this case, the eye mask requires us to have 40 millivolts eye height, and eye width is 0.65 unit interval. Here is a summary of what's required based on the standard of the data rates, eye height, and eye width. The reason why 24 gigatransfer was chosen was because it gives us a little less eye width. Now the conclusion for this slide is that while the simulation condition is noiseless and jitterless, even with that condition, the eye is almost closed. This is bad news. To open up the eye to solve any signal integrity problems, we have to find the root cause. Now first, let's dig a little deeper into the eye diagram. Here is a comparison between nearby channels and TX simulated eye and the expected eye. We'll notice by comparing the simulated and expected that the eye level on the simulated side is a little thicker than what we expected. We expect a nice clean level on the one level, but the simulated shows a little thicker and not as clean. That is unexpected. What's our theory then? What can be causing this? Let's see. We have 3 different traces and 3 different input data, PRBS, coming in. If they are close enough to each other, with the aggressor coming from both ends of the victim line, there's a good chance that the near-end crosstalk would be showing up in the eye diagram. So this is our theory. Our theory is that it is the crosstalk from nearby TXs that's creating the unexpected eye. Now, how do we test this theory? Let's see. We'll confirm it by first having all the traces very far away, like so. There are 10 traces width apart, very far. Then we'll bring them in to 1 trace width apart and see if the near-end crosstalk is creating the thickening of the eye levels. First, we see that when the traces are far apart, hey, everything looks clean, no unexpected things happening. But as soon as we bring the spacing to 1 trace width apart, there it is. The eye levels got really thick because of the crosstalk is coming through. And of course, it also shows on the waveform right there. This is the near-end crosstalk when the traces are close. Next, we'll see on the RX side, we talked about the TX. The simulated received eye looks something like this, and the expected, of course, is an open eye. Upon investigation and observation, we'll see that, hey, during the crossings, the simulated transition has some unexpected spikes, peaks over there. And hey, what could be causing this? Could it be also crosstalk? Let's check it out. The theory is it is the crosstalk from nearby TXs that creates the unexpected peaks. How do we test this theory? Let's do the same thing as we've done before, where we have the traces far apart, where they are 10 trace width apart. Then we bring them in, where the spacing is now only 1 trace width. The far apart we expect to be really clean, and as expected, very clean. Now when they are close, we should see something different. Boom. Sure enough, when we bring the traces close, the received waveform is different. If the received waveform is different, that means, hey, the received eye will also be different. Now we have learned that these are the result of the far-end crosstalk that's generating those peaks in the eye transitions. Okay, so far we have discussed that when the traces are close, there are different crosstalk that's happening, and here are the crosstalk signatures. On the near-end side, we have the thickening of the levels. Yes, thickening of the levels. On the right is the foreign crosstalk signature, and that's going to happen during the transitions. Now, if you change the length of the traces when they're not all the same length, you can potentially move these peaks into the middle of the eye. I've done it, and the eye will collapse in the vertical. All in all, we've learned that when the eye levels are thick and the foreign eye has peaks in the transitions, traces are likely close enough to induce near-end and foreign crosstalk. Now, so what? What are we going to do? But before that, if you have a keen eye, you'll notice between the foreign crosstalk example that I've shown and the simulated eye, something is different. Specifically, is right here. We're seeing some rise time degradation in the simulated eye. And yes, you are totally correct if you're thinking that. Because on the left, the foreign crosstalk example, I simulated with a lossless line. And on the right-hand side, I simulated with a lossy line. So now the next thing we'll talk about is the frequency-dependent loss, which will cause the rise time degradation. Now, the second part of finding the root cause is we will look at what's causing the frequency-dependent loss. Here is an example of a received waveform after a lossless channel. Here's another example of a received waveform after a lossy channel. We can see that it is the loss that is creating the rise time degradation. But what about the loss? Let's take a look at the spectrum. Shown here is the spectrum of the lossless channel and a lossy channel. In the gray in the background there, we can see the lossless channel, and the blue is lossy channel. We see that this low-pass filter of an interconnect degrades the fast rise time. The fast rise time, the edges, is all the high-frequency components. And we can see that the frequency-dependent loss is attenuating the high-frequency content. Here is a waveform and the eye of the eye after a lossy channel. And the channel behavior looks like this. It's a low-pass filter where it attenuates the high frequency a little more and low frequency not as much. Now you might be thinking, if frequency-dependent loss reduces eye height and eye width, what would happen if a frequency-independent loss were to be the channel? That's a very good question. Here I have an example of a lossy channel with constant insertion loss across all frequency. And the result is, if we have constant insertion loss, the entire spectrum is reduced the same way. So only the amplitude will be reduced, as shown here. Frequency-independent loss does not degrade the rise time. It only reduces the eye height, but not the rise time degradation. So it is truly the frequency-dependent loss that's degrading the rise time. All right, so far, we have talked about how we send the signal through the turning transmission lines, and we observe the eye mask, crosstalk signature, and rise time degradation. All these interesting signatures we have learned to identify the SI problems when they arise. Now, believe it or not, UCIe standard provides you with some SI checks as well. It is called the voltage transfer function that I've mentioned a little while ago. And here is what it looks like for VTF loss on our current channel. The current channel looks like this in a VTF chart. The red line is the VTF loss. We want to make sure that we stay above this. And the green is the RX Theta 7 VTF loss line. As I mentioned, we want to stay in here, this green area to pass. It is clear that we're not passing. Our current channel is not passing the loss line check because we have a lot of frequency-dependent loss, the rise time degradation. Now we also expect our channel to fail the crosstalk test. Let's see. Here's the crosstalk test. We want to stay below the VTF crosstalk line, which is right here. That's our data. We need to stay in here, and very clearly that we're not. So as we expected, our current channel fails the crosstalk line check as well. How was it calculated? You might be thinking, it looks great that we can use VTF to assess our channel. So what it's doing in the background is, hey, we'll have a source and connected to it a received signal. And the rest will be terminated if they are in the standard package. Now we have set up the voltage transfer function calculation. We can start looking at the VTF loss definition. Looking at the source and the receive, we will perform this ratio, V receive over V source, and take the power of that and take the log of that to get the frequency dependent loss right there. We have a different calculation for terminator channels. Now here is some VTF loss metric for the standard package. For the VTF crosstalk definition, we will still have the source and received, but this time we focus on not the direct receive, but all the other ones out there. What we'll do is we'll have the sum of all these squared power ratio and add them all together. And here's some of the VTF crosstalk in dBs for different data rates for reference. All right, moving on. Now we know the root causes. We can improve the I by eliminating them. Let's see how we do that. Right now, our VTF crosstalk look like this with a 2.2 trace width apart. What we need to do is to reduce the crosstalk, so we will pull the traces far away to 3x and to 5x. And we would expect we will get closer and closer to passing as we increase the spacing. Let's see, when we increase it to 3 trace width, we're closing in on the passing line, and boom, when we are 5 trace width apart, we pass that VTF limit line for crosstalk. Similar thing for the I. As we increase the spacing, we should see the I slowly opened up. And there it is. The I really opens up when we reduce the spacing between the traces. Finally, I want to show you the timing margin, minimum timing margin, starting at 2.2 trace width apart. That's 0.2 picosecond. As we increase the spacing, we should expect the minimum timing margin to increase. Now in the middle, a little more spacing. The timing margin is at 1.8 picosecond. And finally, when our spacing is 5 trace width apart, the minimum timing margin is 3.8 picosecond. So definitely better I and increased margin as we increase the spacing between the traces. We would expect the increase of spacing have little to no impact on loss, because loss depend on length and not the spacing. However, we should expect that at high frequencies, the coupling introduced and reduced would have some impact. So here is the VTF loss plot. As we see the spacing go from 2.2, 3 to 5, we don't see drastic change on the loss, but we do see the reduce of coupling at higher frequencies. Now, to fix the loss problem, we will have to shorten the length. Here is the spacing maintained at 5 trace width apart and different length from the longest reach for standard package, 25 millimeter, to 20 to 10 millimeter. Now we finally pass at 10 millimeter. This tells us that for this material selection and this geometry, we can only afford a short reach channel. That's very important to note. We can see that we started out with the I almost close with these metrics, 25 millimeter, 2.2 trace width apart. Once we fix the root cause, increase the spacing, shorten the length, hey, our I is open, which tells us the important thing about reducing the root cause, the coupling, and loss. Okay, are there other ways? Assume the channel cannot be changed. Is there other way that we can improve the I? Yes, by using equalization. Here is a TX de-emphasis example where we'll look at and use de-emphasis where we will pre-attenuate the low frequency content, because we know that the interconnect will attenuate the low frequency less. What's going to happen is the transfer function of the FIR of the de-emphasis looks something like this, and this side we were pre-attenuating the low frequency. And here's our Nyquist frequency for reference. So you can see that the emphasis is actually trying to maintain the Nyquist frequency components while attenuating low frequency. Now, TX equalization is recommended for 16 gigatransfer per second, and they must be supported at 24 and 32 per UCIe standard. Here's what the waveform is going to look like. I'm comparing the original waveform and the 2.2 dB de-emphasis waveform. We can see that over here, the de-emphasis is pre-reducing the low frequency content, and A, for keeping the high frequency content because it's all in the rise time. And here is before our 2.2 dB de-emphasis. Because of the different levels from de-emphasis, the eye should also look different than what we had before. And sure enough, we can see that here are the pre-reduced low frequency content, and the high frequency content is preserved in de-emphasis. All right, here is what it looks like after TX de-emphasis, the eye at TX, and boom, the received eye, it opened a little bit, but not too much. This tells us that, hey, the crosstalk, they cannot be equalized away, and you just need to fix the root cause. That is the best practice to solve any signal integrity problems. All right, I think right now our signal integrity journey is complete, where we look at the 20 transmission lines and send in signals, look at the received. We learn about the TX eye diagrams, VTF loss, crosstalk, and received eye diagrams. Now let's talk about what software you should look for and what in the software you should look for so you can produce all of these signal integrity metrics. Here are the key attributes. First, it's gotta be standard focused. Eric always says to me, my advisor, don't work for the computer, let the computer work for you. And here is you want to find a standard focused software so the software is working for you. Number two, make sure you know that the software can perform TX, RX terminations and equalizations because it is in the standard. And also by doing that, you'll be able to explore design and solution space. Thirdly, is the die-to-die interconnect extraction modeling. I'll show you in the demo how Keysight EDA can do this so you can understand what you're dealing with, right? The spacing is important as we see, and the length is important. How do you look at your layout and use EM extraction to get those information? The software should also be able to provide you with what I have shown, the die-to-die channel link from TX all the way to RX, so you can identify the problems early or reproduce existing problems. Finally, of course, the usability integration is very important, so then we don't have to work for the computer. Now here's a demo of the chiplet PHY designer from Keysight EDA that really matches with all those key attributes.
Welcome to Keysight EDA Chiplet PHY Designer demo. In this demo, I will show you how to set up a chiplet simulation with a die-to-die interconnect EM model as the channel. We will look at the resulting eye and compare it to the UCIe eye mask. Shown here is the layout of the die-to-die interconnect. This is a standard package designed with UCIe bump map. With SI Pro, we can convert the layout and stack up into a 3D representation. We will later use the 3D EM simulation result in our chiplet simulation. To set up the chiplet simulation, we'll find the chiplet PHY Designer palette. Let's place a chiplet setup component as well as the chiplet simulation. Double-clicking into the chiplet PHY setup lets you choose the standard, data rate, and package type you are working with. To use our EM simulation results, we drop the post layout component and configure the component with appropriate input files. Pin names and net names should come across nicely from the EM simulation result. Next, we need to place die number 1 on the schematic. You can select your favorite IBIS model to simulate in the chiplet die component after setting up the IBIS files and enabling the signals you want to simulate. Clicking Next brings you to the model selection. All the enabled signals will be here for you. Let's repeat the process for die number 2 on the right-hand side. Select, place, and configure. With Chiplet-Phi Designer, making connections is very simple. First, click on the wiring button, then the components. A dialog will pop up to connect all 16 nets with one click. This smart connection speeds up the setup time. Now, we need to specify what signals to probe. The chiplet probe is the component for that. In chiplet probe, we can select the signals and the measurements we want to see. Of course, we can also set up the UCIe iMask and check if we pass the iMask test. After selecting the signals and measurement, we can hit the Simulate button. Expecting the eyes to be open, we plot the eye and the mask in the data display. Sure enough, the eye is open. Once we finish the eye simulation, we are halfway to the voltage transfer function. Starting from the previous schematic, I will replace the Chiplet-Phi simulator with an AC simulator. Clicking into the Chiplet-Phi setup to configure the voltage transfer function. First, we will name a CSV file as part of the VTF setup. And click Generate. This VTF setup is automatic and ready for the simulation. The auto-generated batch simulation for VTF is in the top right-hand corner. Because the traces are 5 trace width apart, we expect the crosstalk to be under the limit line. Our expectation was correct. I think the loss line will be above the limit line. Indeed, we passed both limit line tests. This concludes the demo for Chiplet-Phi Designer. Thanks for watching.
All right. Here is a quick recap of what we have discussed today. We started today by talking about the monolithic die designs and how it is important to transition to chiplet designs because it is maximizing the wafer usage and it has a higher yield, lower cost, and it's very easy to scale. That's why the industry is shifting to chiplet designs. We looked at the die-to-die communications. It is very important. And we know there are several other standards out there that is going to be facilitating the adoption of chiplet. Second, we dug pretty deep into the electrical layer specifications by using an example. Looking at the full link from the TX to the RX, we learned that there are some modules in UCIe, different data rates. We have TX equalization, voltage transfer function VTF, 4 clocks, quarter rates, and half rates, and then terminations. We know that, hey, for advanced packages, you need to leave it unterminated. Finally, the signal integrity insights are here. The most important one being rule number 9. You have to anticipate before you measure or simulate. We took a look at the near-end crosstalk, far-end crosstalk, and the frequency-dependent loss and how it impact the eye. And also, the de-emphasis, how the TX de-emphasis pre-attenuated the low-frequency content to open the eye at the receiver. We also learned that increasing spacing is great to reduce coupling, reduces channel length, reduces loss, and most importantly, hey, it is best to find the root cause to fix the problem. For the future of chiplet design and the standards, so far they have standard package, advanced package, UCIe. They're working on a 3D packaging and the relevant specifications. And I know there are a bunch of wires, BOW, also working on standards. Intel recently joined the CHIPS Alliance so then they can make AIB, Advanced Interface Buses. I would expect that all the standards to have ways to work with each other. So then the entire chiplet design ecosystem will be more robust and interchangeable. And that is all the presentation for today. I'm now open for questions. Thank you.
All right, Tim, great presentation. We've already got some questions coming in. You ready?
Beautiful.
Okay. Yeah. So we've got a bunch of questions here. This first one, they're saying, I see the VTF chart begins at -5 decibels at DC. Is that due to the geometry? And then they're saying clearly a substrate level or interposer level trace cross section is very small, causing depreciable DC resistance. Seems to be a major part of the challenge with UCIe. Any thoughts on that one?
Yeah, Alan, thanks for a great question. That's one of actually questions I guess a lot when I interact with customers. It is because the resistance a lot at the DC level. That's why you're totally right that it's capturing the more resistive trace at the DC for UCIe standards. That's correct.
Okay. All right, great. Next question here is when I calculate VTF in chiplet phi designer, do I have to enter the equations to calculate the decibel numbers for VTF loss and VTF crosstalk?
Ooh, you know what? I had to do that when I first started working with UCIe, but the beauty of Chiplify Designer is that it does everything in the back end. So all you have to do is set it up, set your interconnect up, and once you set your interconnect up and the simulator up, it's one click to get to the VTF solution. So no, it's not hard. It's very easy, barely inconvenience.
Okay. All right. Excellent. Another question here. They're wondering, could UCIe become the generic interconnect, for example, replacing the interface to an HBM?
Ooh, Aaron, that's a great question. I would say, if I have to guess, it would be tough for UCI to become the generic interconnect for everything because all interfaces have to work with each other. Say the HBM has a certain standard and they have a lot of people, engineers working on make sure the interoperability is great. Now, can UCIe work with HBM? I think that is the future, where UCIe will be interfacing with HBM or CXL or PCIe. That is all in the works. And in the future, like I mentioned in the presentation, all the standards have to have a way to work with each other, to interface with each other.
All right. All right. Excellent. Next one. What does the UCIe standard say about receiver equalization?
That's a very important question to ask because sometimes you have to, sometimes you don't. The answer to that question is that for certain data rates, higher data rates like 24 gigatransfer or 32, it is recommended to have it, but sometimes you don't. So it depends on how great your interconnect design is and how much you're willing to give up for your margin. But yeah, so the standard dictates what you can and cannot do on the receiver equalization side. So make sure you contact the expert in your company, you talk to your simulation experts to make sure that your software can perform receiver equalization because in the standard they ask you to have it. Thank you.
Okay. All right. Another one. The two clock signals are labeled clock P and clock N. Are these a pair of differential clocks?
Oh, Michael, that is a very good observation on the slides. Your attention to detail is great. Yes, it supports differential clocks. UCIe supports differential clocks. And one thing I would also mention is not only does UCIe supports differential clock, it also has the capability of half rate clock, which is your typical clock, and the quarter rate clock, which is a clock that's slower. So that would help out the signal integrity on the higher end where you have your 24 gigatransfer, 32 gigatransfer, and now the standard body is talking about 48 gigatransfer. So with the quarter rate clock support from the Chiplify designer, you'll be able to simulate all these before you go into production.
Okay. All right. Super. Well, Tim, I think we've run through most of the questions here. If somebody wants to get started with Keysight or find out more, what do you recommend?
Oh, the thing to do will be use the handout to get it started on learning about the chiplet and the signal integrity analysis on it. Then in keysight.com, you can search chiplet file designer and you should be able to see a lot of information. Also connect with me on LinkedIn. I usually do a lot of posts on chiplets, and we have other information on our other products like EP scan, electrical performance scan. So I'm a signal integrity application scientist. That's my specialty. So you can connect me on LinkedIn and definitely go to keysight.com, search chiplet file designer. Thank you, Scott.
Awesome. Thank you, Tim. Great stuff today, and appreciate all your insights here in the Q&A as well. Really appreciate it. All right, and before we wrap up, we have one more piece of business, and that is the Amazon gift card prize drawing. And the winner of that $250 Amazon gift card is Chris Shelsky from New Hampshire. Congratulations to Chris Shelsky. We'll be in touch to get you your card. And with that, on behalf of the Smart Brief team, I want to thank Keysight Technologies for making this event possible. And thanks as always for attending and for your great questions. That's going to conclude today's event. Have a fantastic rest of your day.